Hey you guys, it's Professor Schmidt here to solve this first problem at the end of chapter problem solving set. So the problem reads, the following data shows different mating results between milkweed plants that had either yellow or white flowers and tall or short stems. Determine the dominant allele for the two traits and indicate the parental genotypes for each hypothetical cross. So I got to tell you guys, sometimes what goes wrong with these problems goes wrong before you even try to start solving them. In other words, you read this big long thing and by the end of it, you're sort of already getting possibly confused about what it's going on. What are they giving you? What are they asking you? So I think it's worth taking the time. I know there's often not a lot of extra time on an exam, but basically the bottom line is they're telling you certain information, right? That it doesn't matter that it's a milkweed plant, really. I mean, it could be anything in this case. But this is a dihybrid cross, right? It's dealing with flower color, and it's dealing with the stem length, all right? And we're going to have two possibilities at the flower color locus, yellow or white, and two possibilities over at the stem length, either tall or short, right? So that's what you're being given. What they want from you is two things. Determine the dominant allele for the two traits and indicate the genotypes of the parents for each one of these crosses, A through F. So, it's a reasonable amount of crosses. Maybe on an exam they'd only give you one or two, but it's good to practice with all these different type of things. Now, I also have to tell you guys that it depends on the situation, but there's not always an absolute correct way to do a problem. What I mean is that multiple strategies might yield the proper result. So I'm going to give you a way that I think is the best and the most time-saving. Just be clear that if someone teaches you a different way, then it's not necessarily wrong. It's just a way of getting to what we need to get to. All right, so what I'd like to do is start out, because if we need to know the genotypes, we really need to know which one is dominant and which one is recessive first at both loci. Now, you could look at all this data, and I'm sorry if I'm emphasizing it too much, but the way you start off is really going to determine the way you end up. If you start off wrong, then that's it right there, right? You can work for a half hour on this, and if your beginning either assumptions or setup is incorrect, you're going to be in trouble. So it's worth taking the time to make absolutely sure what it is you're doing, what they're asking, etc. Now here's the way I would look at this. These are independently assorting traits, right? So remember, just for the same reason you can do the line method, you can think of them separately. And I think in terms of figuring out the dominance, it's very smart to think about them separately. So here's the logic that I am going to look for without even looking at the data, honestly. If you crossed, think about this. Don't even look at the data. I'm just giving you the idea. Say if you see a cross that's a white times a white, right? If white was recessive, let's just guess that, your cross would be like this, right? Wouldn't it be true that all offspring would have to be white? Well, it would be true if that was in fact recessive. The same idea. If you see a cross that's a yellow times a yellow, if that one was recessive, I'm just making up the letters here, then all offspring would be yellow. So to me, it's as simple as looking for these crosses where it's the same thing times a white times a white or a yellow times a yellow, and just seeing what the result is, and then doing the same thing for tall and short. So let's see if we can find that. Well, conveniently enough, we see down here in cross F, for this part it doesn't matter if you go in order, you're just looking for data. It's a white times a white. So the question is, do you see any yellows from that cross, or are they all white? Now, the categories up here are giving you both of them, yellow, white and tall, yellow short. Now we're only worried about the color. So when you cross white times white, what do you get? You get white and tall, which we don't care about tall, and white and short. So basically all of them are white. That seems to imply that it's the white that is in fact recessive. It doesn't prove it, But here's what we want to do now, is find a yellow times a yellow, right? And let's use the first one. We're crossing yellow times yellow. Remember, we said if the yellow was in fact recessive, you'd have to get all yellows in the offspring. But this is really the telling point here. In this offspring, you get a lot of yellows, but you also get some whites. So I hope you can see why that really does prove that the yellow, in this case, yellow is dominant and white is recessive. I really think that's the best way to do it. And also for some of you, I don't really think shortcuts are always the best thing to do. But for some of you, you could just scan that data and see that in like 20 seconds. It doesn't mean that you shouldn't explore it a little bit further. But if you're thinking along those lines, you may very well just be able to, see it in that data set. And if you are under severe time pressure, sometimes you don't have time to really work it all out. That might be all that you need. Okay, so we know that yellow is dominant, white is recessive. I'm going to erase some of this stuff so that we can look for what the situation is with the tall versus short. And I didn't look at this one on purpose because I want to sort of solve the problem with you. So remember, we want to look for ones that are the thing by itself. In other words, by itself meaning times itself. So there's only one here where there's a short times a short that I see. And you'll notice that all the offspring, remember, sorry, I should have erased this as well because we're not interested in that anymore. All the offspring are short, right? Maybe yellow and white, but we don't care about yellow and white now. They're all short. So we're sort of, again, getting the idea. Short is recessive. By the way, guys, you can't tell just from that. I hope you can see that. It could be a pure breeding line of the dominant. So that's why you have to then go for the tall and see if you can find a situation where you're crossing a tall times a tall and getting the short. And to do that, we may as well go back to the beginning because you cross a tall from a tall. You do get a bunch of tall offspring, but you also get some short offspring. And that would be impossible if tall was recessive. So we're going to then say that tall is dominant. So this answers the first part of the question, because that's what they wanted. Determine the dominant allele for the two traits. They didn't specifically ask which is recessive, but I mean, if you know the dominant one, you also know the recessive one. So we now have tall is dominant and short is recessive. And why don't we now decide then that big T is going to equal tall and little t is going to equal short, based on the common convention that Mendel used. And we furthermore know that yellow is dominant, so we'll make big Y yellow, and we'll make little y white. So now what we have to do is indicate the parental genotypes for each of these hypothetical crosses. So to do that, we need to go down a bit and have some room. And we can figure out the genotype by looking at the results. So keep that in there so that we can see the classes. So in the case of, it's very pivotal and important that we understand which one is dominant and which is recessive before we do that. That's why we did that part first. So now that we know yellow and tall are dominant, right, we have a cross up here, A, which is yellow tall times yellow tall. For A, so the question is, what do we know? We know that each of these parents, just by being yellow and tall, has to have at least one big Y, right, and one big T. The question is, what's in here? It's not necessarily true that you'll always be able to figure this out, but in this case you can. And again, I would do it by, well, let me just illustrate a situation where there's two ways you can do it here. When you look at the data here, I don't know if you can see that obviously, but that's a 9:3 to 3:1 ratio, right? So again, if you're really pressed for time, you could just remember that the way to get a 9:3 to 3:1 ratio is by crossing double heterozygotes, right? And it turns out that those are the genotypes of both of the parents. If you wanted to go ahead and do it the way I had said, by keeping them both separate, you could do that as well. And you could say, look, I'm crossing yellow times yellow right here. Let me get rid of this. Crossing yellow times yellow. And what am I seeing in the offspring just with respect to color? I'm seeing 122, I just quick did that in my head, that are yellow, and 42 that are white. And that's a 3-to-1 ratio, in essence. So that again tells you that, in other words, there's really only two choices, right? Let's get this down because this is going to come into play often. Since this question mark is really all that we're trying to fill in, I mean, it's either big Y, or it's big Y, yellow Y. If it's big Y, well, if they were both big Y, that would be a pure breeding line and you couldn't have this situation, right? But you guys know the way you get a 3-to-1 ratio, and that's by crossing two heterozygotes. So that's another way of looking at it and filling in that there must be little y's there, right? And there's so many ways to think of this. Because you do end up getting a certain amount of white offspring, right? The white offspring have to be little y, and they have to get one of those from each of their parents. I'm sorry if I really hope it's not getting confusing, but it's just that there's so many different ways to look at this and to figure it out that I want to just get you comfortable with, not necessarily memorizing one specific way, but just being comfortable with the whole situation. So for the exact same reason, the tall times the tall, if you go ahead and look at that, you'll find a 3-to-1 ratio there. So with respect to problem A, the parents are both double heterozygotes, right? Okay, good. Now, the reason I'm going to erase is because I want to keep this data up here. You can always pause if you need to, or back up if you need to look at this again. So we got the answer for A. Now let's do B. Yellow and tall times yellow and short, right? So my suggestion to you is before you even look at the data, think about what you know just by virtue of the thing being yellow and tall. We know that it's got one big Y and one big T, right? The one that's yellow and short, though, we know is in fact like this. So when something is exhibiting the recessive trait, as you know that has to have two of the small letters, right? So here's the question. We're crossing a yellow times a yellow. What do we get in the offspring in terms of color? Well, we only get two classes, which is interesting, and those are all yellow, and those are all yellow, right? So there's a situation here where it's a little bit hard to tell what. Here's my point. If this one was big Y times big Y, you'd get all yellow. But there are two other situations where that could happen. If this parent was a heterozygote and this parent was a homozygote, all of the offspring still would appear yellow, right? And the same goes if, the same situation in reverse. So that's one of these cases where you really honestly can't tell whether or not, the parent, either parent, one of them has to be homozygous, but the other one might be heterozygous, and there's no possible way that you can get around knowing that. So you'd have to say on a test, based on the evidence, there are a couple of possibilities. The same is not true, though, with the tall times short, right? We're crossing a tall times short, and really the only question here is that which we didn't fill in. We know there's two little t's going to be there. We don't have to do this all the time, but if you make a little Punnett square, we know that's on one side. We know there's at least one big T from there. So the only thing is, the question is what's here. And if we look at the data, only with respect to tall and shortness, we find that check it out, about half of them are tall and about half of them are short. What does that imply? Well, first of all, if this was a big T, all of the offspring would be big T, little t, and they would all appear tall, right? So what that really proves is that this parent right here is a heterozygote at the T locus, big T, little t. If you fill in the boxes, you'll find that those are the ones that are looking tall, and these are the half that are looking short, okay? So there's a little question here about the y locus in terms of you can't say exactly what it is, but with the t locus, it has to be this big T times little t, all right? Now, by the way, since they're separate, well, I'm sorry, that doesn't apply in this case. Strike that from the record, please. All right, hopefully now we're on a roll. We're going to go ahead and do C. We've got a yellow tall times a white tall. So again, I would recommend, I'm sorry if it's getting laborious. A lot of these problems do get tedious and laborious, but they're still fun. Something's yellow and tall, that's what we know. And if something's white and tall, we know from that locus that it's little y, and has at least one big T. So we're going to do exactly what we did before. We're going to say we crossed a yellow, which could either be, it's really not that bad, guys. There's two choices, right? Here, there's only one question about the yellowness. It's, is that thing a homozygote or is it a heterozygote? I hope you could see. If this position was a homozygote, all the offspring are going to be yellow. If it's not, based on the idea we just did, you're going to see 50-50. So what do we in fact see? About half the offspring are yellow and about half the offspring are white, right? So what does that tell you? That tells you that with respect to the yellow locus, for the same reason as the Punnett square we just drew, this yellow parent has to be a heterozygote. Now, as far as the tall locus, it's tall times tall. All of the offspring also look tall. So, guys, we have a situation here that's very similar to the one we just had, sort of just in reverse. There are different possibilities. This could be big T times big T. This could be big T times big T, little t, or the reverse. It's really exactly the same as the last situation we had at the y locus. There's no possible way to determine what's going on from this data. Now, just for the record, if they gave you an F2 generation from these parents, it might come out which one of these was true or which was not. But you don't have that here, so you can't tell what you don't know. I think that makes a lot of people nervous because it's sort of like, gee, I need a definitive, absolute, definite answer. That would be nice, but unfortunately sometimes you really just can't. It's as simple as that. All right, we're ready to do D. It's going to be so sad when this is over, because I could just do this all day, and I'm sure you feel the same way. I'm going to change to blue just for fun. So I thought I could change to blue, but it's not letting me. All right, how about black? So now we've got a yellow tall times a white tall, right? And in fact, if you notice, that's the exact same cross that we just had in C. So you may think that that's redundant, but look, now the data is different. We're going to be able to tell something. What do we know just by virtue of something being yellow and tall? If it's getting boring, guys, it's a good sign because it means you understand it. If it's white, it's little y. So this is the same original setup we had for C, right? Given that it's the same cross. But now when you look, it's yellow times white. But when you look at the offspring, you see 122 of them being yellow. And got to do this math in my head. 117 of them being white. That's basically a 1-to-1 ratio. So that tells you that that position we're questioning is a little y, right? But look at the tall situation. Look at the tall situation, which is that. The ratios in tall are, there's 179 there, I believe, to exactly 60 tall to short. That's a 3-to-1 ratio. And the only way to get that is big T little t times big T little t. All right, so in this case, you can, with absolute definite certainty, say that these are the two parents. The yellow and tall one was a double heterozygote, and the other parent is little y, big T little t. All right, we're almost there, guys. Let's do E. Yellow short times yellow short. So sometimes you get a break, not that often, but every now and then. I think I'm going to be allowed blue now. Okay, so yellow, obviously, again, we have this question, but short, we know, is little t times yellow short, right? There really is no question about the short locus. Just to make sure, all of the offspring, if this is true, should be, in fact, be short, right? And if you look, they all are short. So that's done deal right there. Yellow times yellow, there's a question, and let's look at the offspring in terms of who's yellow and who's white. Okay, so, well, there's still only two classes, right? And it's a 3-to-1 ratio of yellow to white. That strongly, well, implies it's big Y times big Y, right? So as we go along, this isn't quite as difficult or challenging as you might think. It depends on the data, perhaps, obviously. All right, last one. We've got a white tall times a white tall. Now, with the white, we have a situation where we know it's like that. Almost the opposite of before. You'll remember we looked at this cross before and noticed that all of the offspring are in fact white, which goes along with this idea, so there's no question about that. But we do see a 3-to-1 ratio of tall to short, right? And again, we know the only way to do that is to do that. So we basically have little y, big T little t, times little y, big T little t. Interestingly, you know, they're both the same phenotype and they end up both being the same genotype, but they didn't have to be, right? It would depend on the data. All right, well, hopefully now you're comfortable with doing that type of problem. You'll probably see something like that one time or another, and that's all I have to say about that, in the words of a famous movie character. All right, guys, see you soon.
Question 2 says that the ability to roll one's tongue is a dominant trait in humans. Draw out the pedigree for the following scenario and answer the accompanying questions. Demi, a female who can roll her tongue, marries and has children with Jamal, who cannot roll his tongue. The couple has 2 sons and 1 daughter. Of all the kids, only 1 son cannot roll his tongue. So let's take account what information they're giving us. They say that the ability to roll your tongue is dominant, so let's define that as big R. And we'll say that is rolling tongue. Now I went out and drew the pedigree, but let's fill it out together. So Demi is the female, and she can roll her tongue, so we're going to shade her in. Jamal can't, so we'll leave him blank. And the couple has 2 sons and 1 daughter, and all the kids, only 1 son cannot roll his tongue, so therefore the other son and the daughter can both do that, so let's fill them in. Now, because it's a dominant trait, that means that the individuals who aren't affected must be homozygous recessive. So let's write that out. Jamal is little r, and the 1 son who cannot roll his tongue is also little r. Now, we don't know if the affected mother, what her genotype is, which is what the first question is asking. But the 2 children that are affected, because the father can only give a little r allele, then these 2 affected children must be carriers. So they are big R, little r, big R, little r. So the first question says, what is Demi's genotype for the tongue rolling gene? Now, because she had an unaffected son here, that means one of these little r gametes had to come from the mother. And because she's affected, she must have at least 1 dominant allele, and she must have that little recessive allele to give to the unaffected child. So for A, Demi's phenotype is RR. Now it says for B, if the couple's daughter later marries someone who cannot roll their tongue, what is the probability that their firstborn will be a boy who cannot roll his tongue? So this is the daughter here. She is big R, little r. And they're saying if she marries and has children with someone who cannot roll their tongue, which is little r, little r. So if you want to do simple Punnett square for this cross, the mother can either give a big R or little r, and the father can only give little r's. So here is a half chance that the offspring will be able to roll their tongue because they're big R, little r, and a half chance that they won't be able to roll their tongue because they're homozygous recessive. But the question asks also, what is the probability that it will be a boy who cannot roll his tongue? So the probability of being a boy is 1/2, and then the probability of not being able to roll your tongue is 1/2 again. So therefore the total probability is 1/4. So that's the answer right here. A common grandmother of 2 first cousins has a rare recessive condition that causes her to fall asleep every hour. Neither of the cousins has the sleeping disorder, nor do any of their relatives. If these first cousins had a child together, what is the chance that the child would have this disorder? So let's take note that this is a rare recessive disorder. So we can define that as the allele. Let's call it F for falling asleep. So to have this disorder, you have to be little f, little f. So I went out and drew a pedigree, and this is a little arbitrary because the parents of the first cousins could either be sisters, they could be brothers, or they could be brother and sister. So, but this is the common grandmother here, and she is the one who has this condition. So let's shade her in. And therefore, we know her genotype is little f, little f. So let's see. Because also it's rare, we're assuming that anybody marrying into the family who doesn't have this disorder doesn't have the allele for this disorder either. So we can assume that this grandfather was big F, big F. So that means that their children must both be big F, little f, or carriers of this disease. And again, because it's rare, these men that they married were assuming that they're big F, both of them. Okay, so the problem's asking, what is the chance that their child of the first 2 cousins will have this disorder? So in order for their child to have this disorder, both parents must at least be a carrier of the disease allele, or else they would never pass it on to their child. So the probability of this male being a carrier is 1/2, because you're doing big F times big F, little f, which is his parents. So he has a 1/2 chance of being big F, little f. And the same goes for this female. Her parents are big F times big F, little f. So she has a 1/2 chance of being a carrier. Now, if both these parents were carriers, then you would be doing big F, little f, times big F, little f, which is a monohybrid cross, and would therefore be a 1/4 chance of the child being little f, which equals the falling asleep disorder. So for the total probability of this child having the disorder, you have to include the chance of the father being a carrier, which is 1/2, the chance of the mother being a carrier, which is another 1/2, and then the chance of 2 carriers having an affected child is 1/4. So the total probability is 1/16. And as you can see, even with recessive alleles, this is why common law doesn't allow first cousins to marry most of the time, because there is a genetic risk of a child having this. Even if it's a rare recessive disease, there is a chance that this child will be affected with it. Question 4 states that parents who both exhibit the dominant curly dark hair have a child with straight light colored hair. What is the genotypes of the parents? So let's first define what our alleles are. So we're talking about 2 different traits, even though they both are for hair. You have both the shape, curly or straight, and you also have the color. So let's see, the curly is dominant, so let's call that big C equals curly, whereas little c will equal straight. And then for the color, dark hair is dominant, so let's do D equals dark, and then little d will equal light colored. So both parents have curly and dark hair, which means they have to have at least one dominant allele for each trait. And this is the parental generation. And it says they have a child who has straight, light-colored hair, which means that they are recessive at both gene loci. So the offspring is little c, little c, little d, little d. Now, in order to get this individual, this offspring individual, that means that each parent must have the recessive allele for both traits, or else where else would this individual get it from? So the parents here must both be big C, little c, so that they can give their little c's to the child, and big D, little d, so that they can give their little d's to the child. So the genotypes of the parents both are heterozygous at both genes. Question 5 asks, what is the probability that the following cross would yield a big A, little b, big C, little c offspring? So for this question, the way I would like to solve it is to do the simplified line method that I showed you in the earlier problem-solving videos. And that is where you look at each separate gene loci, A, B, and C, separately as if they're a monohybrid cross, and then multiply across the probabilities. So let's first look at A. Both parents are heterozygous at the A locus. And for the offspring that we're looking for, it's heterozygous as well. Now, you should know from simple monohybrid Mendelian crosses, the probability of getting a heterozygous offspring from a monohybrid cross is 1/2. And that's because 2 out of the 4 offspring have big A, little a. So that is the probability of getting big A, little a. Now for B, again, both parents are heterozygous. And they want the probability of the offspring having little b, little b. Now again, this is a simple monohybrid cross, so the probability is 1/4 to get the homozygous recessive genotype. And then for C, both parents again are heterozygous, and they want probability of a heterozygous C offspring. So again, that is 1/2, big C, little c. So for the line method, what you do is multiply these probabilities across to get the total probability. So you have 1/2 chance for the A locus, 1/4 from the B, and 1/2 from the C. Multiply that across, you get a total probability of 1/16, and that's of getting this genotype. Question 6. Based on the information in the following pedigree, would you predict that the disease is dominant or recessive? Does the mutant allele seem to be rare or common in the population? Please give reasoning. So first, let's focus on if it's dominant or recessive. The first thing that jumps out at me is that affected individuals come from unaffected parents, and the same over here. Now, from the problem-solving videos on pedigree analysis before, this is a clear indication that it could be recessive. So let's guess recessive. And then we do the genotypes to see if that actually works. So if it's recessive, that means that the affected individuals must be homozygous recessive. So let's just call this allele R. So these individuals must be little r, and the same for here. Now, in order to have affected children, that means that both parents must be carriers. So these parents here must be big R, and big R, little r, and the same for these parents here. We know that none of them are little r, because they're not affected. And also, the fact that they do have unaffected children is also another clear indication of that. So this individual here, it could be big R, but it could also be big R. So let's just write a dash. And we already know that this individual right here is a carrier to have affected children. So genotypically, this seems to work that, yes, it is recessive. Now the second part of the question is, does the mutant allele seem to be rare or common in the population? Now usually, even if a pedigree doesn't say it, you assume that the disorder is rare, so that anybody marrying in is assumed to be homozygous dominant. However, in this case, you see that this individual here married into the family and had this disease allele, the recessive mutant allele. And also, depending on which parent you look at as coming into the family, they both have the mutant allele too, So therefore, we would say that it's actually common in the population. So it is recessive and common.
Hello, it's Professor Schmidt to do this true-false section of the end of chapter problem set. So these actually aren't so bad, especially since you've been doing these things over and over and over again. We'll do it as simply as we can. So this is all true-false, but we want to make sure we understand the rationale. Why? The dominant allele always masks the effect of the recessive allele in a heterozygous individual. So that just means randomly using A. If you have an individual that's big A, little a, and you have dominance, masking the effect is one way of saying that basically the organism is going to phenotypically look whatever big A is. And that is true, right? Remember what the definition of dominance is. As long as one of the dominant alleles is there, that's what you're going to see phenotypically. So that's true. Simple as that. Number 2, big A, big B, little b represents a dihybrid individual. Sometimes you'll see different terminologies. We've talked about dihybrid crosses, but a dihybrid individual basically means one that I've been referring to as a double heterozygote. Okay? So since this is big A, big B, it's pure breeding at the A locus, right? So a dihybrid individual would be this. Since that's not what we see, that one is false. This one is just a matter of knowing. Number 3, the first generation of offspring in a cross is called O1. Well, if you knew nothing, that might seem reasonable, but it's false because why? What do you call the first generation of the offspring? That's known as the F1, right? The first filial generation. So far, easy. Easy peasy. Get it? Because of the peas that Mendel used? Anyway, Mendel's first law states that alleles at a particular locus segregate from each other into different gametes. Now be careful about this one. Be very careful, because you could get confused about the first law, the second law, exactly what's going on. Is it mitosis, meiosis? But basically, the first law does say that if an organism, that there are two genes basically for every trait, right? And that when you're making gametes, one goes one way and one goes the other way. So that is definitely one of the things that his first law says. Not the only thing it says, but that is definitely true. A brown-eyed individual's phenotype may be big B, little b. Now, normally, this is one that could confuse you as well if you don't see the magic word here. Because phenotype by definition cannot be big B, little b, right? Phenotype is the fact that it's brown-eyed. So the question's almost, I don't know if it's just dumb or it's trying to trick you. A brown-eyed individual's phenotype is brown. Its genotype could be big B, little b, or big B, right? But here's the key, and they do that to you sometimes just to see if you're paying attention. So the phenotype can never be big B, little b, or any type of expression like that. That's the whole key, that one word in there. And obviously words are important. Who said words mean things? They do, obviously. But I'm just saying it could be easy to say, oh, they must mean genotype, or not even think about it and say, yeah, big B, little b, because you're knowing about the dominance of the brown eyes. Okay, number 6. True breeding individuals with 2 identical alleles for a gene, so like this. In fact, it's fine that they said that, but if it's true breeding, it does have 2 identical alleles, right? So is that a homozygote? Yes, absolutely. Whether it's big A, or whether it's little a, it doesn't matter. But true breeders have to be homozygous, right? And lastly, the product rule is used to determine the probability of flipping heads 3 times and then tails 1 time. The product rule is multiplication. So basically the idea is what's the probability of flipping heads or tails? It happens to be a half in this case, right? Whether it's heads or tails. But if you want this exact sequence, this is what's important. Probability drives some people crazy, But basically, if they just said, hey, you flipped a coin 4 times, what's the probability of getting 3 heads and 1 tail without order? That's a different thing. If you want the order, it says heads 3 times and then a tail. You have to say each individual event is different, and that's when you use the product rule. So the first time there's a half a chance of getting heads, then there's a half a chance of getting heads, then there's a half a chance of getting heads, then there's still a half a chance of getting tails, right? So they didn't ask you to do the problem. The answer of what the probability of that exact sequence is 1/16. But yes, you do use the product rule. So that is true. And while they may talk about flipping coins, this also holds true for example, saying, if you said, what's the probability that a couple has three boys and then a girl? That would be the same exact thing. Okay, well, I hope you've enjoyed this as much as I have. I'm sure I'll see you real soon.